Welcome to section 3.3, the real zeros of a polynomial function. Okay, let's recall if r is a real zero of a polynomial function, f, then f of r equals 0. R is an x-intercept of the graph of f. X minus r is a factor of f. And r is a solution of the equation f of x equals 0. Okay? So we're going to keep all of those facts in mind for this section. Objective 1. Use the remainder and factor theorems. When one polynomial, the dividend, is divided by another, the divisor, a quotient polynomial and a remainder are obtained. The remainder is either the 0 polynomial or a polynomial whose degree is less than the degree of the divisor. To check, verify that the quotient times the divisor plus remainder equals the dividend. This checking routine is the basis for the following theorem. The division algorithm for polynomials. If f of x and g of x denote polynomial functions, and if g of x is a polynomial whose degree is greater than 0, then there are unique polynomial functions q of x and r of x, for which f of x divided by g of x equals q of x plus r of x divided by g of x, or f of x equals q of x times g of x plus r of x, where r of x is either the 0 polynomial or polynomial of degree less than that of g of x. In the equation, f of x is the dividend, g of x is the divisor, q of x is the quotient, and r of x is the remainder. To help you visualize it, we can write it as a long division problem. And we have q of x, and this would be plus our remainder r of x. All right. The remainder theorem states that suppose f is a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Okay. So let's apply this remainder theorem to the next couple of problems. So here we're asked to find the remainder when f of x equals x cubed minus 5x squared minus 6 is divided by, okay, so x minus 2 for a is our factor, which means x equals 2 when we set x minus 2 equals to 0. So we can evaluate f at 2 by substituting 2 in for x. Or wherever I see an x, I'm substituting in 2. So I would have 8 minus 20 minus 6. And that gets me negative 18. Okay? So my remainder is negative 18. Okay? So our x equals negative 18. All right. Find the remainder when f of x is divided by x plus 4. So we'll take our factor, set it to 0, and so x is going to equal negative 4. And we'll now evaluate our f of x when x is -4 by substituting in -4 for the variable x. Then we can simplify. This will equal -64 minus 80 minus 6, which equals -150. So the remainder will equal -150. Okay? The factor theorem states, suppose f is a polynomial function. Okay? Then x minus c is a factor of f of x if and only if f of c equals 0. Okay? So a consequence of the remainder theorem is the factor theorem. And the factor theorem actually consists of two separate statements. It says that if f of c equals 0, then x minus c is a factor of f of x. And if x minus c is a factor of f of x, then f of c equals 0. Or in other words, our remainder will be 0. So now let's solve some problems using the factor theorem. So we'll use the factor theorem to determine whether the function f of x equals x cubed minus 2x squared plus 3x minus 6 has the factor for a, x minus 2. Okay, so in this case, we're going to set x minus 2 equal to 0, and so x is going to equal 2. So we will evaluate 2 in our function. By substituting 2 for all variables x. And then we'll simplify, so that's 8 minus 8 plus 6 minus 6. And so the 8's cancel, the 6's cancel, so that's 0. So because f of 2 equals 0, the factor x minus 2 is a factor of f of x. So we wanted to factor f of x. We know one of its factors. Let's check if x plus 1 is a factor of f of x. So we'll set this factor equal to 0. So we'll evaluate f of x at -1. So we are going to substitute in -1 for every value of x in the function. We'll simplify. So this will be -1 minus 2. This is actually squared. So that's 1. So that's minus 2. And then minus 3 and minus 6. So this will equal -3, -3, -12. So because f of -1 does not equal 0, the factor x plus 1 is not a factor of f of x. And that's what the factor theorem helps us see. So from part A, we learned that x minus 2 is a factor of f of x. But we can now use synthetic division to factor f. Now that we have a factor, we can use synthetic division to help us. So we're going to set up our bar. We're going to place our x in the top left-hand corner here. So that would be 2. Then on the other side, we're going to list out all the coefficients in descending order. So the first coefficient is 1, then -2, then 3, and then -6. So that's 1, -2, 3, and 6. And then we'll do the process of synthetic division. So we'll bring down the 1, multiply it by 2, then add it to -2, multiply it by 2, add it to 3, multiply it by 2, and then add it to -6. So this bottom row here is going to be our quotient. The last value, which here is 0, is going to be our remainder. So q of x is going to equal x squared plus 0x plus 3, which we know simplifies to x squared plus 3. Okay, and then our r of x equals 0. Okay, so f of x in factored form equals x minus 2 times x squared plus 3. Okay, now q of x, just want you to note, is considered a depressed polynomial. Okay, because it's 1 degree lower than the original function. So the original function f of x had a degree of 3, and so the quotient will be 1 less than that degree, which is 2. But how many real zeros can a polynomial function have? In counting the zeros of a polynomial, we count each zero as many times as its multiplicity. So a polynomial function cannot have more real zeros than its degree. Objective 2. Use Descartes' rule of signs to determine the number of positive and the number of negative real zeros of a polynomial function. So Descartes' rule of signs says that suppose f denotes a polynomial function written in standard form. The number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals the number less an even integer. The number of negative real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of negative x, or else equals that number less an even integer. All right, so let's see how this is used. I believe an example will help us see this more clearly. So we are going to determine the number of real zeros of f of x. Okay, so we want to determine the possible number of real zeros that are positive and that are negative. So when you're using the Descartes rule of signs, I recommend identifying your positive real zeros first and then your negative. So to find the positive real zeros, we're going to take our function f of x. I'm going to write it out here. 3x to the fourth squared plus 5x minus 2. And I'm going to identify all of the variations in the sign of the non-zero coefficients. In other words, I'm going to identify all of the sign changes of the coefficients. So our first term, 2x to the 6, is positive. The next term is negative 3x to the 4th. The sign has now changed from positive to negative. Now, if I go to my third term, it's a positive x squared. So my sign again has changed from negative to positive. 5x is positive, so my sign has not changed. And then my constant, negative 2, has a negative or subtraction sign, and so my sign has changed. So I have 1, 2, 3 variations. So there are possibly 3 positive real zeros. But it's not just 3. It could also be equal to the number less an even integer. So an even integer is divisible by 2. So, in other words, I'm going to subtract 2 from this value. So this function could have 3 positive real zeros, or it could have 1 positive real zero. So when you're trying to find the number of positive real zeros, you take your function and you determine the number of sign variations. Okay, so that's the number you start off with. That's the number of positive real zeros. Now the other set could be equal to that number less than an even integer, so that number minus 2. Okay, now let's find the negative. So to find the negative, we are going to find the number of variations in f of negative x. Okay, so we are now going to multiply all of our x variables by negative 1. Okay, so let's do that. So 2 times negative x to the 6 minus 3 negative x to the 4th plus negative x squared plus 5 times negative x minus 2. Now, if I have an even power on a negative value, I know my sign will always be positive. The only time my sign will be negative is if my power is odd. So my first term here will remain 2x to the 6. My second term will be 3x to the 4th. My third term will be x squared. My fourth term would be negative 5x and then negative 2. So the only term that changed was a 5x to the negative 5x. So a neat little trick is that when you are trying to find your negative real zeros, all you'll have to do is change the sign of the terms that have an odd power. So in our original problem, the only term that had an odd power is 5x, because x is to the first power. Okay? So now we need to identify the number of variations in the sign of the non-zero coefficients. So my first term to my second term changes signs. My second term to my third term changes signs. And my third to my fourth also changes signs. So I have 3 variations here. So this is similar to the positive. So we could have 3 negative real zeros or 1 negative real zeros. Okay, awesome. So we know though that the degree of our polynomial is 6. So this function has no more than 6 zeros. Okay. Objective 3. Use the rational zeros theorem to list the potential rational zeros of a polynomial function. So the rational zeros theorem says that let f be a polynomial function of degree 1 or higher of this form f of x, where each coefficient is an integer if p divided by q in lowest terms is a rational zero of f, then p must be a factor of a sub 0, so that's your constant, and q must be a factor of a sub n, so that's your leading coefficient. Okay? All right. So for our problem here, we are going to list the potential rational zeros of f of x. So notice that the polynomial has integer coefficients, all integer coefficients. So we have 2, -1, -1, and 4. The first thing you need to do in finding the potential rational zeros is identify your p and identify your q. Okay? Now, p must be a factor of a sub 0. So a sub 0 is our constant, and our constant here is 4. So we know p equals 4. A sub n is our leading coefficient, and our leading coefficient is 2. And n here is our degree, which is 5. Okay? So now we need to find p and q in lowest terms. So let's first find the factors of p. So p is 4, and the factors of 4 are 1, 2, and 4, plus or minus. The factors of q, which is 2, are 1 and 2. So if I wanted to find p divided by q, I would take each factor of p and divide it by each factor of q. So I would have plus and minus 1, 2, and 4, and plus minus 1 and 2. So let's first take the 1. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. We take 2. 2 divided by 1 is 2. 2 divided by 2 is 1. We already have that there. 4 divided by 1 is 4. 4 divided by 2 is 2. We already have that there. Okay? So we have a potential of 8 possible rational zeros. These are our potential rational zeros. All right. Caution. So it may be the case that the function does not have any rational zeros. So the rational zeros theorem does not guarantee rational zeros. It states for a polynomial with integer coefficients, if there is a rational zero, it is one of those listed. So for example, -1 may or may not be a rational zero of f of x equals 2x to the 5th minus x to the 4th minus x squared plus 4, because -1 is in the list of potential rational zeros. However, we know 3 is not a rational zero of f because 3 is not in the list. Polynomial division, synthetic division, or substitution can be used to test each potential rational zero to determine whether it is indeed a zero. To make the work easier, integers are usually tested first, and then you test the rational or fraction zeros. So in objective 4, we're going to actually now find the real zeros of a polynomial function. And it's broken down in steps for us. So let's find the real zeros of the polynomial function f of x equals 3x cubed plus 4x squared minus 5x minus 2. We're going to write f in factored form at the very end because we would have all the zeros. So in step 1, we're going to use the degree of the polynomial to determine the maximum number of zeros. Well, the degree of our polynomial f of x is 3. So we have a degree of 3. So there are at most 3 real zeros. Okay. Step 2, use Descartes' rule of signs to determine the possible number of positive real zeros and negative real zeros. So we'll take our original function to find the positive real zeros. And remember, for Descartes' rule of signs, we are trying to determine the sign variations in the function. So the only sign variation or change that I found is between the second term and the third term. So that means there is one positive real zero. Then for the negatives, we are going to change the sign of all the terms that have an odd power. So that would be the first term because it has a power of 3. And that would be the third term because it has a power of 1. Okay. So now we want to identify any sign changes. So between the first and the second, we have a sign change, and between the third and the fourth, we have a sign change. So there are potentially 2 negative real zeros, or no negative real zeros. And how do I know that it's negative? So remember, in Descartes' rule of signs, right, we are looking at the variations of the signs to determine the number of potential positive or negative real zeros. Or, all right, we take that number minus 2 to determine the number of possible positive or negative real zeros. Now, for positive real zeros in this problem, if we subtract 2 from 1, we would be a negative 1, and you can't have a negative number of positive real zeros, which is why for the positive, it's just 1. Okay? All right. So, step 3. If the polynomial has integer coefficients, use the rational zeros theorem to identify the rational numbers that are potential zeros. Use substitution, synthetic division, or polynomial division to determine whether each potential rational zero is a zero. If it is, factor the polynomial function. Repeat step 3 until all rational zeros of the polynomial function have been identified, or until the function can be factored. Okay? So let's find the potential zeros of our function. All right, so I'm going to just write our function out here for us. So f of x equals 3x cubed plus 4x squared minus 5x minus 2. Okay, and I need to first find a sub 0, which is my constant. That's -2, so that's p. A sub n, and n here is the degree, which is 3. So that is going to be 3, which is Q. So now I need to find the factors of P and divide it by the factors of Q. So I will have plus and minus. The factors of -2 or 2 would be 1 and 2. The factors of Q would be 1 and 3. Okay? So to list out all of my ratios, I'll have 1 divided by 1, which is 1. 1 divided by 3, which is 1/3. 2 divided by 1, which is 2. And 2 divided by 3, which is 2/3. Okay? So now we need to test these zeros. We need to see if one of them is actually a 0. Remember in step 2, the possible number of positive real zeros is 1, and the possible number of negative real zeros are either going to be 2 or none. Okay? So let's test out a positive 1. So I'm going to set up my synthetic division. I'm going to place 1 up here in the top left-hand corner. On the other side, I'm going to list all my coefficients in descending order. So that would be 3, 4, -5, and -2. I know my last value that I get here in the box is going to be my remainder. And I want that remainder to be a 0, because if it's a 0, that means 1 is a 0 of the polynomial function, and then I have my first factor of my function. So let's start the process. We'll bring down 3, multiply it by 1, which is 3, add it to 4, which is 7, multiply it by 1, which is 7, add it to -5, which is 2, multiply it by 1, which is 2, add it to -2, which is 0. Okay? And so I see here I have a remainder of 0. So if I were to write f of x in factored form, I would have my depressed polynomial 3x squared plus 7x plus 2 multiplied by my new factor x minus 1. Okay? Because 1 is a 0 and its factor is x minus 1. So now I can continue the process and test some other zeros with 3x squared plus 7x plus 2. Or I can use other methods to find the factored form of this quadratic. So 3x squared plus 7x plus 2 is factorable. And when I factor that quadratic, I will get 3x plus 1 times x plus 2. And I'll bring down the x minus 1. And so now I have f of x in factored form. So the zeros of f are x equals 1, x equals -1/3, and x equals -2. Are the zeros of f. Okay. And so that matches what our possible zeros were. We have 1 positive, and then we either had no negatives or 2 negatives, and it ended up being 2 negatives. Okay. So note that the equation 3x squared plus 7x plus 2 equals 0 is called a depressed equation of f. So any solution of this equation is always going to be a 0 of f. Okay. So in summary, the steps for finding the real zeros of a polynomial function are: step 1, use the degree of the polynomial to determine the maximum number of real zeros. Step 2, use Descartes' rule of signs to determine the possible number of positive real zeros and negative real zeros. Step 3, If the polynomial has integer coefficients, then we can use the rational zeros theorem to identify those rational numbers that potentially could be zeros. And then we can use substitution, synthetic division, or polynomial division to test each potential rational zero. Each time zero is obtained, a factor is found. We're going to repeat step 3 on the depressed equation. So when searching for zeros, use factoring techniques already know when possible. All right, so let's now solve this problem. Okay. Please note that we don't have the steps here as we did in the last problem, but I have the summary here at the bottom to help us through the process. So for our function, we have 2x to the fourth minus x cubed minus 5x squared plus 2x plus 2. Okay? So right off the bat, I know that this is a polynomial of degree 4. Where did I get 2 from? I think I was looking at the 2's and I said 2. But correction, this is a polynomial of degree 4, which means there are at most 4 real zeros. Okay? That's what step 1 is. Use the degree of the polynomial to determine the maximum number of real zeros. So that is step number 1. Okay? Step number 2. We need to use Descartes' rule of signs to determine the possible number of positive real zeros and negative real zeros. So let's take our function f of x, and we are going to identify all of the sign changes. So first to second, I have a sign change. Third to fourth, I have a sign change. So there are either 2 or 0 positive real zeros. Okay, so the number of variations or the number of variations minus 2. So 2 minus 2 is 0. Next, I'm going to find the number of negative possible real zeros. So to find that function, I'm going to change the sign of every term with an odd power. So that would be the second term, and it would be the fourth term. Okay? So now I want to identify the sign changes. So that would be from the second to the third and from the fourth to the fifth term. Okay. So I also have 2 or 0 negative real zeros. Okay. All right. So before we go into testing anything, we now need to go into step 3. Okay. So if the polynomial has integer coefficients, we can now use the rational zeros theorem to identify those rational numbers that potentially could be zeros. So this function has all integer coefficients. There's no decimals, no fractions. Okay. So we can identify our P and our Q to help us find our rational zeros, our possible rational zeros. Okay. So this is step 3. So a sub 0 is 2, that's our constant, so that's P. A sub n, which is a sub 4, is 2, and that's our Q. So P divided by Q would be the factors of 2 divided by the factors of 2, which would be 1 and 2 and 1 and 2. When we divide each number in the numerator by each number in the denominator, we'll get 1, 2, and 1/2, obviously plus or minus. So we have 6 possible rational numbers to choose from. Remember, out of these 6, we could have at most 4 real zeros. Okay. So now we need to test. All right. And I'm going to start off with 1. All right. So we are going to set up our synthetic division. 1. I'm then going to list out all of the coefficients in descending order. So I'll have 2, -1, -5, 2, and 2. Remember that my last value here is going to be the remainder. I want the remainder to be 0, because if it's 0, then I know this potential 0 is a 0 of my function, and therefore will help me create a factor of my function f of x. All right, so let's do the process. Bring 2 down, multiply it, add, multiply, add, multiply, add, multiply, add. So 1 is a factor, a real 0 of f of x. So our quotient, which is our depressed polynomial, comes out to be 2x to the third plus x squared minus 4x minus 2. Okay. So we can now continue testing this polynomial with another potential 0, or we can use other methods like the factor form. All right, we can use factor by grouping in this process by grouping the first 2 terms, the last 2 terms, factoring out the GCF between both of the groupings. Remember, we want to get the same expression in the parentheses, which is 2x. We now have 2 terms. The GCF between both terms is 2x plus 1, leaving us with x squared minus 2. Okay. So we have now factored f of x. So f of x in factored form is now x minus 1. That's what we got here when we tested it, because we got 0, so we know 1 is a 0. Its factored form is x minus 1. And then we have 2x plus 1 and x squared minus 2. Okay, awesome. So this is the factored form of f of x. One more thing to note, x squared minus 2. X squared minus 2 has no real solutions. All right, no real solutions. So we keep it as x squared minus 2. Okay, so the real zeros of f would be x equals 1 and x equals -1. These are the zeros of f. Okay, alrighty. Objective 5, solve polynomial equations. So we want to, for this example, find the real solutions of the equation. Now, the real solutions of this equation are going to be the real zeros of the function f of x equals 2x to the fourth minus x cubed minus 5x squared plus 2x plus 2. Okay? So if we can find the real zeros of this function, then we've found the real solutions to the equation. Okay, and this is the same function that we just looked at. And so the real zeros are 1 and -1/2. Thus, the real solutions of the equation let's write it out. 2x to the fourth minus x cubed minus 5x squared plus 2x plus 2 equals 0 are 1 and -1/2. Okay, so a quadratic factor, ax squared plus bx plus c, is irreducible if it cannot be factored over the real numbers. That is, if it is prime over the real numbers. So every polynomial function with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. A polynomial with real coefficients of odd degree has at least one real zero. Okay? And we just worked through a problem similar to that. And the irreducible quadratic factor, the example could be from our last problem, the x squared minus 2 equals 0. That is a quadratic factor, and it is irreducible. So that's an example of what that would be referring to. Objective 6, use the theorem for bounds on zeros. So a number m is an upper bound to the zeros of a polynomial f if no zero of f is greater than capital M. The number lowercase m is a lower bound of no zero of f is less than lowercase m. Accordingly, if lowercase m is a lower bound and capital M is an upper bound to the zeros of a polynomial function f, then lowercase m is less than or equal to any zero of f that is less than or equal to capital M. For polynomials with integer coefficients, knowing the values of a lower bound lowercase m and an upper bound uppercase M may enable you to eliminate some potential rational zeros. That is, any zeros outside of the interval lowercase m, capital M. Now, I probably read all that and you're like, okay, cool. What does that mean? Well, let's go into the theorem. So we're going to let f denote a polynomial function whose leading coefficient is positive. If capital M is greater than 0, is a real number, and if the third row in the process of synthetic division of f by x minus m contains only numbers that are positive or 0, then m is an upper bound to the zeros of f. If lowercase m is less than 0, is a real number, and if the third row in the process of synthetic division of f by x minus m contains numbers that alternate positive or 0 and negative or 0, then m is a lower bound to the zeros of f. I know that probably didn't help you much. So let's do an example. All right. So for this problem, we are going to find the upper and lower bounds of zeros. So to solve the problem, or this problem, we are going to find the upper and lower bounds of the zeros of the polynomial f of x equals x to the fourth minus 5x squared minus 36. Okay? So first thing that we need to do is identify the coefficients of the polynomial. So the coefficients of the polynomial are 1, 0, -5, 0, and -36. Why? Well, x to the fourth has a coefficient of 1. Then we have a missing term, x to the third. That has a coefficient of 0. That's why it's not there. Then -5x squared, coefficient -5. Then we have x, the linear term. It's not present, so that's 0. And then -36. So that's where we got all of our coefficients from. Next, we need to test integer values with synthetic division. So what integer values are we going to test? Well, we're going to test those possible zeros. So our constant a sub 0 equals -36, which is p, and our leading coefficient is 1 equals q. So I'm going to take all the factors of 36 and divide it by all the factors of 1, which is 1. So in other words, all my potential zeros are all of the factors of 36. Okay? Now the factors of 36 are going to be 1, 2, 3, 4, 6, 9, 12, 18, and 36. I believe I got them all. 1, 36, 2, 3, 4, 6, 9. Yep. All right. So what we're going to do now is we are going to test some of these integers. I'm not going to test them all because the goal is to find the upper and the lower bounds. Okay? So I'm going to choose some positive and I'm going to choose some negative. Okay, so the positives are going to tell me my upper bounds and my negatives are going to tell me my lower bounds. Okay? So for R, I'm going to test 1, 2, 3, and I'm going to test -1, -2, and -3 just for this example. Okay. So the goal is if all the numbers in the bottom, excluding the remainder, are non-negative when we perform synthetic division, then the value of R is an upper bound. If all of the signs in the bottom row of our synthetic division alternate, so no zeros allowed, then the value of R is a lower bound. Okay, so let's test this out. All right, so let's first test out 1. Okay. And then I'm going to put my coefficients. And then I'm going to do my process. So 1, 1, 1, 1, -4, -4, -4, -4, and my remainder is -40. So my coefficients of q of x, that's what this is, my last row, are 1, 1, -4, and -4 with a remainder of -40. Now let's test 2. 1, 0, -5, 0, and 6. So bring down the 1, multiply, add, multiply, add, multiply, add, multiply, add. Okay, this one too. My remainder is -40, so I know it's not a 0. So 1, -4, and 1, 2, -1, -2, -40. All right, let's try 3. 1, 0, -5, 0, -36. So bring down the 1, multiply, add, multiply, add, and multiply, add, multiply, add. Oh, I got 0. So I have 1, 3, 4, 12, and 0. Notice that all of these coefficients are positive. These are all positive. Since they are all positive, we know that 3 is our upper bound. Okay? So if all the numbers in the bottom row, excluding the remainder, are non-negative, meaning all positive, then the value of r is our upper bound. So we know 3 is our upper bound. So now that we know our upper bound, we need to now find our lower bound. So let's start at -1 and test. So we have 1, 0, -5, 0, -36. So 1, multiply, add, multiply, add, multiply, add, multiply, add. So we have 1, -1, -4, 4, and -40. So that one is a no. Let's try -2. 1, 0, -5, 0, -36. And I'll also test -3 too, so I'll just set that up. 1, 0, -5, 0, -36. So 1, multiply, add, multiply, add, multiply, add, multiply, add. So that one, -2, is not our lower bound. Remember, for the lower bound, all the signs in the bottom row alternate with no zeros. Alternate with no zeros. So they alternate signs. So let's try 3. So, or sorry, -3. So 1, -3, add, or multiply, then add. So it's 4, 12, 12, 36, and 0. So we have 1, -3, 4, -12, and 0. So this right here is alternating signs. So because that's alternating signs, we know that -3 is our lower bound. So 3 is our upper bound and -3 is our lower bound. So upper bound is 3 and the lower bound is 4. So these are the bounds for the potential zeros of f, or actually any zero of f is going to be between 3 and 4. Sorry, not 3 and 4. 3 and negative 3. Oh, where did I get the 4 from? There we go. So any real zero of f is going to be between negative 3 and 3. I have to correct that. All right. Objective 7. Use the intermediate value theorem. So the intermediate value theorem says, let f denote a polynomial function if a is less than b, and if f of a and f of b are of opposite sign, there is at least one real zero of f between a and b. Okay? So in our first visual here, we have a function. Okay? And we know f of a is going to be this point here. So this is a and f of a. And then this point up here is going to be b and f of b. Okay. If the point a f of a is on one side of our axis and b f of b is on the other side of the x-axis, then there has to be a real zero between those 2 points. Because in order to go from below the x-axis to above the x-axis, you have to cross the x-axis. Therefore, there's a 0, because the x-intercept is also the real zero of the function. Okay, so there's at least one real zero. At least one. All right. For b, we have something similar, depending on which point you're looking at. But in this case, we have 3 real zeros. So we could potentially have 1 real zero, or we could have multiple real zeros between the 2 points. But as long as a point is above and a point is below, there's at least 1 real zero. So for this example, we're asked to show that f of x has a real zero between 0 and 1. Okay, and our f of x is 2x to the 4th plus x squared minus 1. So to determine whether a real zero exists between 0 and 1, we're going to substitute in 0 and 1 into our function. We want to then look at their signs. If they are opposite signs, then we know that there's a real zero that exists. Okay, so let's find f of 0. We'll do that by substituting in 0 for x. So we have 0 squared minus 1. So that would be minus 1. Then we can evaluate f of x at 1. So we're substituting in 1 for x. Okay. And so now we have 2 plus 1 minus 1, which equals 2. So, because, and I'll write this out for you so that you can reference it, because f of 0 is less than 0 and f of 1 is greater than 0, the polynomial function f of x has at least one real zero between 0 and 1. It has at least one real zero. Alright, so next we're going to look at the steps for approximating the real zeros of a polynomial function. So step number 1 says find two consecutive integers a and a plus 1 for which f has a real zero between them. Step 2, divide the interval between a and a plus 1 into 10 equal subintervals. Step 3, evaluate f at the endpoints of each subinterval until the sign of f changes. Then by the intermediate value theorem, this interval contains a real zero. And then step 4, now divide the new interval into 10 equal subintervals and repeat step 3. Step 5, continue with steps 3 and 4 until the desired accuracy is achieved. Note, if at step 3 the value of f equals 0, the process ends since that value is a 0. So here in our example, we're asked to find the positive real zero of f of x equals 2x to the fourth plus x squared minus 1. And we know from our previous example that there exists a 0 between 0 and 1. Right? That's how we use the intermediate value theorem to locate where that 0 exists, and it exists between 0 and 1. So for step number 1, we are going to find two consecutive integers, a and a plus 1, for which f has a real 0 between them. And we know a positive real 0 exists between 0 and 1. If you didn't know the values, you would use the upper and lower bounds that we worked on to try and find a potential 0 that could exist. All right. Number 2, step 2, divide the interval a and a plus 1 into 10 equal parts. So our first interval would be 0 to 0.1. Our second interval will be 0.1 to 0.2. Third interval, 0.2 to 0.3. Then the next one, 0.3 to 0.4. Then the next one, 0.4 to 0.5. Then we would have 0.5 to 0.6, 0.6 to 0.7, 0.7 to 0.8, 0.8 to 0.9, and 0.9 to 1. And now we have our 10 equal subintervals. All right. Okay, so now step number 3. We want to evaluate f at the endpoints of each subinterval until the sign of f changes. Then by the intermediate value theorem, this interval contains a real 0. So we're going to evaluate f at the endpoints of each interval. Okay? Well, starting off with our endpoint f0, we know that equals 1 from a previous problem. So then we'll need to find f of 0.1, f of 0.2, f of 0.3, f 0.4, f of 0.5, f 0.6, f 0.8, or sorry, 7 and then 8. Yeah, 7, 8, and then 9. And then we know f of 1, which is 2. Okay, so we know our endpoints. So in between our endpoints, we're trying to find where the sign changes. So once the sign changes, then we can stop. All right. And so you could do this by hand and substitute in 0.1, 0.2 into your function and then evaluate it. But to quicken the process or make the computation just a little bit easier, we are going to use our calculator. Okay. So in our calculator, we are going to enter in our f of x into y equals. So we'll go to y equals, and we'll enter in 2x to the fourth plus x squared minus 1, and press enter. Okay. Now we're going to go to the table. So second graph to go to the table. And we see here our table goes by ones. We want our table to go by 0.1. So we need to change our table. So we're going to go second window to go to that table set. We want our table to start at 0. So we'll enter 0 there. And we want the change in our table to be 0.1. Okay. So now we're going to press second graph. And so now we see here all of our values. So you will write out all of the answers on your notes for all of these values. And then we'll be able to identify where the sign changes. And so in just looking here at this table, I see that the sign changes between 0.7 and 0.8. Okay, 0.7 and 0.8. Thus, I know that my 0 is going to exist between those two values, and I can then continue on to step number. Okay. So let's write out these values on our notes so that we have them to reference. So 0.1 is negative 0.9. Next is negative 0.957 and negative 894 and negative 789 and negative 0.625. And then 0.6 is negative 0.381. And then we have negative 0.03. And then 0.08, we have 0.4592. And so we can stop right there. We don't need these because our sign changes between 0.7 and 0.8. Okay. So thus, the 0 exists between 0.7 and 0.8. Okay. So now for step number 4, we're going to divide this new interval into 10 equal subintervals and repeat step 3. Okay. So now we're going to take our new interval and we're going to divide it into 10 new subintervals. We'll have 0.7, 0, 0.71, 0.71, 0.72, 0.73, 0.7. Oh, it should be a 2. It should be a 2. 2 and 3, and 3, and then 4, and then 4, and then 5, and then 5, and then 6, and 6, and then 7, 7, then 8, and then 8, and then 9, and 9, and then 0.8. All right. So in repeating step number 2, we're now going to, step number 3, we're now going to find the endpoints of each of the subintervals. Okay? So we'll find f of 0.70, f of 0.71, f of 0.72, and we would continue on until we got to the end. All right, I'm just going to do the first 5 so that I can then utilize my calculator to determine exactly where the change is occurring. Okay, so let's pull up the calculator. All right. So now I want to change my table a little bit because we have a different starting value and we're going by a different change in our table. So let's go to table second window to go to the table set. I'm going to start at 0.70, and then my table change is going to go by 0.01 this time. I'll press enter to lock that in, and then second graph to go to my table. Okay. And so now I see here, right up here at the top, well, one, I have all my y values for the first 10, which is beautiful. But right here at the top, my eyes go directly to that change. At 0.7, I have negative 0.03, and then at 0.71, I have a positive 0.0123. So I know that a 0 must exist between these two values. All right, so let's write that down in our notes. So we have 0.3 and 0.012. So I actually did not need all of these. So I recommend utilizing your calculator, setting it all up. Identify where your y values are for your endpoints, and then where the change occurs. That way you don't have to list out all of the endpoints, but if your problem does request that, then you'll know how to get it. Okay. So does 0 lies between 0.70 and 0.71. All right. Awesome. So now we can go to step number 5. And step number 5 says to continue with steps 3 and 4 until the desired accuracy is achieved. So since our problem tells us to find the positive real 0 correct to 2 decimal places, then we are just going to choose the 2 decimal places for our 0. So we're not going to continue the process. If it said 3 decimal places, then we would do this process again. And we'll try and get as close and as close and as close as possible to our answer. So we will say, therefore, zero is 0.70. Alrighty, so that will be our 0 for our function, our approximated real 0 for our function. All right. Great. So that concludes the end of section 3.3.